Hello everyone, this video is about electromagnetic waves. So let's understand how they are formed and how they look like, and also its relation to the light and its various applications. So James Clerk Maxwell was one of the most important physicists of the 19th century, and he came up with a set of 4 equations that describes the electromagnetic fields. Well, let's not go through all the equations, but let's go through the things that he discovered with these equations. Okay, so first, that the electric field lines originate on positive charges and terminate on negative charges, and that the electric field is determined by the force per unit charge, and that the strength of this force is related to the electric permittivity of free space. Okay, this first part here talks about the electric field, how we calculate it, and its force. The second thing he discovered is that the magnetic field lines are continuous, having no beginning or end, and that the strength of this force, the magnetic force, is related to the permeability of free space. Okay? The third thing is that the changing magnetic field induces an electric field, and the direction of the electromotive force opposes this change. And finally, that the magnetic fields are generated by moving charges or by changing electric fields. So see that these two statements here, the two first statements, they describe how the electric field and magnetic field are formed and how we calculate their strength, alright? And the two last statements is the relation between the magnetic field and the electric field. So see that one can induce another by moving charges, right? And that's exactly what are electromagnetic waves. We have magnetic fields, okay, that's inducing an electric field, or the opposite way, we have an electric field that's inducing a magnetic field. So how these electromagnetic waves are formed? Well, let's start by thinking about a point charge, an electron here, and this electron emits an electric field around it, okay? And we represent it with this vector E here. Now, let's put this electron in a metallic bar and attach it to an alternate source of current. Okay, so when we turn this source on, the electron starts to move up and down. Okay, and so the electric field vector is also moving, okay, up and down with the electron. So the electric field is oscillating, all right? So if we plot this electric field here over time, we have something like this, a sinusoid, right? And according to Maxwell's equations, this change in the electric field produced by this moving charge here induces a magnetic field, okay? So this is an electromagnetic wave. We have this electric field that's inducing this magnetic field, alright? It's also important to know that both are perpendicular, okay? If you have this magnetic field over here, this electric field over here, the magnetic field is perpendicular, and also the direction of propagation is perpendicular to both, okay? By using his equations, Maxwell was able to calculate the speed, okay, the propagation speed of an electromagnetic wave using this expression here. So it's basically 1 over the square root of the permittivity times the permeability of free space. And he found out that the speed of propagation is 3 times 10 to the 8th meters per second. And that's exactly the speed of light, right? Well, in fact, the light is a visible electromagnetic wave, okay? So the only thing that changes here is the frequency or the wavelength of the electromagnetic wave. So the visible spectrum from red to violet is around this wavelength here, from 10 to the negative 2 to the 10 to the negative 6 meters, right? This is the visible light. But the electromagnetic field, okay, the waves actually, we can change its frequency or the wavelength. So we are changing from a spectrum that is not visible anymore. So if we go beyond 10 to the negative 2 meters, we go infrared, okay, below the red spectrum. And if we keep going, here we have bigger and bigger wavelengths. So we have microwaves, that's around 1 meter, and radio waves, okay, that's 10 to the second to 10 to the 4th meters. If we go beyond the violet, we have ultraviolet. And from here, we have more energetic wave, electromagnetic waves. Okay, you have X-ray and gamma rays that we need to be very careful about, right? And, well, this is the entire spectrum of the electromagnetic waves. And these are the wavelengths that are very useful to us. Okay, we have various applications. So one of the applications we have for electromagnetic waves is to transmit information. So let's imagine again that metallic bar, okay, attached to the alternate current source. So we have the electron there that's vibrating, all right? So it's inducing an electromagnetic field, so we have an electromagnetic wave. If we put another metallic bar near the source here, this electron will start to oscillate according to this electromagnetic wave because it's being induced by this wave here. So see now that we are transmitting information from this metallic bar to this metallic bar through electromagnetic waves. And that's exactly how radio antennas work. We have an antenna that's transmitting the information through the waves, and the radio, okay, with its antenna that's receiving this information. And that's exactly how we transmit information via radio. So that's it. I hope you like, and see you next time.
Now that you've learned the theory, it's time to put that to practice. Check out our next videos for practical problems.